Our next talk is a generative model for punctuation dependency trees. The presenter is Lisa Lee.
Hello, everyone. Thanks for coming. I'm Lisa, and this work is done jointly with Ding Chuan and our advisor, Jason Eisner. We focus on the generative model for punctuation in dependency parsing. So the NLP community has been neglecting punctuation. The tree banks simply treat them as ordinary tokens. But the few linguists who have bothered studying punctuation believe that it is a layer of language with its own rules. Just like morphology, phonology, syntax, semantics, and pragmatics, punctuation marks are not just words. So what rules does punctuation play? Punctuation marks are correlated with the syntactic tree structure, and they could help us parse. When we generate text in summarization, translation, or editing, we'd better know where the punctuation goes, or we might have tragic results. And let's look at one example. So we start from a segment of dependency tree. The dependency structure of the word tokens is well annotated. But what about the 3 commas in the sentence? The first comma delimits the left boundary of the appositive. The third comma delimits the right boundary of the relative clause. But the middle comma kind of does both. It could pair up with either the first comma, or it could pair up with the second comma. So which association choice should we make? We are stuck in a dilemma, and this cannot be the right way to handle punctuation. In the treeback annotation manual, where we consider commas as regular words, we have to make a hard choice. However, we lose the generalization that a relative clause should be surrounded by commas, not just terminated by a comma. Really, there should be 2 commas here. So now we have a theory that appositive and relative clauses can each be delimited by 2 commas, and that sentences tend to end in a period. But the problem with our theory is that it's not yet generating English. Normally, English doesn't have 2 punctuation marks in a row. And we need to theorize the second step of string rewriting that applies at each slot between words. We should rewrite 2 consecutive commas into a single one. Or rewrite a comma and a period into a single period. Now the green punctuation marks look like grammatical English. In fact, we are not the inventor of these rules. Linguists like Nürnberg deduced them from observation. But we are going to learn them automatically from data. And we will learn this type of rules for 5 languages, including but not limited to English. I said that English collapses multiple adjacent punctuation marks, but not always. Here, we keep both the period and the right quote from the quotation marks around Excalibur. Logically, the period should go last, but every language has its own system, and American English moves the period inside the right quote. This case actually needs 2 added because we also still have to deal with the comma. So first, we again use the period to absorb the comma, and second, we swap the quotation and the period. This swapping is also described by Nürnberg as quotation transposition. So there could be variation in a way a tree is punctuated. For example, what if we want the sentence to be a question? Then the root is associated with a question mark rather than a period. And we do not swap positions between a question mark and a closing quotation mark. So we'll introduce a systematic and probabilistic approach to discover punctuation rules for a more general set of punctuation vocabulary. So to quickly summarize, punctuation marks are not just words. They do not belong in the tree, and only underlying punctuation marks are in the tree, where they surround certain phrases. So in other words, we have enhanced the previous correlation between punctuation and tree by splitting punctuation into 2 parts, underlying and surface. The underlying form needs to explain the surface punctuation and in turn be explained by the tree structure. When we follow the up arrow and go from surface punctuation to recover the underlying punctuation and eventually to recover the tree, we're essentially doing punctuation-aware parsing. And when we follow the down arrows, we generate underlying punctuation from the tree and the surface from the underlying punctuation. And now, let's focus on this generative process. Step 1 is attach, and step 2 is rewriting. So in the attach step of the generative story, we traverse the tree, and each node independently chooses which left and right punctuation pairs to generate. Root can generate an empty string at its left boundary and a period at its right boundary. In this case, we end the sentence with a period, and as usual, the beginning of the sentence is the empty string epsilon. For a positive, it can generate a left and right comma. In this case, we surround Arthur Pendragon by commas. Similar probabilistic attachment happens for the relative clause. And almost any phrases could be surrounded by a pair of quotations. It's rare, but in this case, it happens for direct object. So how do we parameterize the probability for attach at each tree node? We zoom into a particular example. So this is our feature template. F1 and F2 are atomic features that directly score a pair of punctuation. Features like F3 and F4 help us model that short phrases are less often surrounded by commas, and phrases that already have an internal comma are sometimes surrounded by dashes or semicolon instead to show the hierarchical structure. So we also have further linguistically motivated features, and please refer to our paper for detail. We apply the log linear model to these scores and get a softmax distribution over the candidates. So now we rewrite the blue underlying punctuation to the green surface form. Nürnberg gives a list of rewrite rules for English, and we will learn them automatically for English and for other languages. So a long underlying string like this could result from a deep tree with several nested constituents ending and starting at the same position. And we list a sequence of good punctuation rules that are involved in rewriting these punctuation strings. So we have a sliding window model with a window size of 2 to help us rewrite the sequence of punctuation. For every pair of punctuation marks, our job is to apply the correct rule. And we have to deal with the fact that the rules are not perfect, and the corpus is sometimes noisy, so we make them probabilistic. Also, in this way, it's easier to learn because we could gradually adjust the probabilities, and we could by backpropagating the gradient. But in general, the rules should be mostly deterministic, and we find that they do have low entropy. So to summarize the generative process, underlying punctuation is generated at each tree node. It's not quite independent because of the internal comma feature. So total underlying punctuation at each slot between words is rewritten into the surface punctuation independently. In parsing, we observe the words and the surface punctuation, so they are shaded, and we have to infer the tree and its underlying punctuation. Instead, we'll do an easier version of the problem, where we also observe the gold tree. We are just trying to infer the underlying punctuation according to our generative model. And that's the E step of the EM algorithm. We can then use the inferred punctuation to improve the generative model. That's the M step of EM. So since we are trying to infer from the posterior of the underlying punctuation, one natural method is to do Gibbs sampling. First, we initialize the punctuated tree by randomly sampling the punctuation to attach at each tree node. Second, we linearize this underlying punctuation. We check their compatibility with the surface punctuation, aka will it probably turn into the green punctuation under stochastic rewrite rules. In this example, the first slot is 0 for any setting of parameter, and the last slot is close to 0 once we have trained our model. In the setting of Gibbs sampling, we keep randomly flipping underlying punctuation marks. The flips that increase likelihood are more probable, until we find underlying punctuation that does a good job of predicting the observed surface punctuation. So after 2 flips, For example, we end up in a state where the higher direct object generates a right quotation and the lower direct object generates a left quotation. Now the rewriting step has good probabilities. But the attach step suffers from low likelihood because the quotations aren't matched. After several other flips, we could end up in this state, where both the attach and the rewriting steps are happy. The sampler will spend most of its time in good underlying punctuation like this, and this gives Monte Carlo samples for the E step of EM. So that's just to give you an intuition. We didn't actually do Gibbs sampling because it's approximate and it's really slow. Actually, in the paper, we give an order n dynamic programming algorithm, which is exact and efficient. So the idea is to make a weighted context-free grammar that generates just the possible underlyingly punctuated tree for this sentence. The weights reflect two soft constraints we saw the Gibbs sampler trying to satisfy. And we intersect them to get our context-free grammar. The first constraint is that the underlying punctuation should go with the tree label. So we will write a non-recursive PCFG that generates just the author tree plus stochastic punctuation. It's very easy. The second constraint is that the underlying punctuation should go with the surface punctuation. So we use a weighted FSA at each slot to describe all the punctuation strings that could be rewritten as the surface form. This FSA is actually cyclic because when you see a surface comma, there could be any number of underlying commas. We intersect the PCFG and the weighted FSA to get our weighted context-free grammar. Because it pretty much only has one tree structure, we can find the best underlying punctuated tree or sum over the underlying punctuation in order n time. And please see the detail for this algorithm in our paper. Now we'll discuss two model analysis and two engineering experiments. So the rewriting rules that we learned are consistent with Nürnberg's analysis of English. These are bar plots of the distribution. In the leftmost figure, the input is a comma, comma, and we have high probabilities of collapsing into a single comma. In the middle figure, the input is comma period, and we have high probability of comma absorption. In the right figure, the input is quotation period, and with high probability, we rewrite to period quote for American English, and it stays at quote period in British English. So here's one case study. We find the one best underlying punctuated tree according to our trained model. The adverbial modifier is surrounded by a pair of commas. The tree node nmod is also surrounded by a pair of commas. The tree node ccomp is surrounded by a pair of quotation along with a left comma. As you can see, the underlying punctuation intuitively is compatible with both the tree and the surface. So for a case study of Oxford comma, the best underlying punctuation surrounds the middle conjunct with two commas, but leaves the last conjunct unsurrounded. We experimented with the punctuation restoration task. Assume that we have an unpunctuated sentence with its gold parse tree. We are trying to reconstruct the gold surface punctuation. Our results are in the box. We have a lower error rate than a BioSTM CRF tagger, which struggles with this task and barely beats a trivial heuristic. Since our method relies on having gold parse tree, we also investigate in a case where we do not have perfect parses. This does hurt our method, but even when we don't have the perfect parse, even around an 80% parsing accuracy is good enough for us to reconstruct punctuation better than the baselines. So here's another experiment. If you add it to your writing, you know that English gives you some freedom in how you realize the surface order of constituents. In some of our other work, we learn a stochastic dependent ordering model that we can use to propose rephrasing of a sentence. But if we just use the silly tree bank treatment of punctuation, the results are terrible, as we can see. And we quantify terrible using language model perplexity. The right way to do this is to infer the underlying punctuation at all tree nodes. Like this. And then we can permute the nodes. And finally generate the new surface punctuation in green. And this method generates correctly punctuated sentence as an output. And thank you for listening.
Questions? So you will treat existing punctuation as a part of your observed variables, right?
Yeah.
Okay. This is quite interesting since by adding punctuation, you're essentially enriching the syntactic structure of a parse tree. Have you think more along this line? So in addition to just this delimiter punctuations, think about other possibilities of enriching the structure?
Other possibility of enriching like structure of dependency tree to help parsing? Well, I think like one possible people can certainly explore like the underlying properties of morphology and then incorporate it as part of the parse tree.
Right. People thought about that.
Yeah. Or like another thing that we kind of did is like we can also incorporate like capitalization into the model. It's like a very similar treatment. Like you can kind of treat capitalization as an operator, similar to punctuation, and then that could potentially also help parsing.
Yeah, that's very interesting. Thank you. I didn't see when you do Monte Carlo sampling and when you do dynamic programming, which one works better? I think the dynamic program will work better.
We actually didn't try Monte Carlo sampling in our paper. It's just
Right.
for talk. It's just
Right.
to give an intuition of how the process should work.
Of course. This
Yeah.
makes sense.
Yeah, but of course, dynamic programming should work better because it's exact and it's fast.
exact.
Yeah.
Yes. And for this particular problem.
Yeah.
More questions? Yeah, let's thank the speaker again.
Thank you.
So that's the end of this session.